Hi student, how are you? I hope you're fine. So today we're going to solve a problem, an initial value problem. So the problem is given as first order initial value problem, which is given by y prime equals to negative 2y plus exponent negative x. Okay, this is the problem that we want to solve, and the initial condition is given as y at x equals to 0 equals to 1. Now we're going to solve this by using h equals to 0.1 to find the value at y. Let me see, 0.1 maybe, 1.2. How about that? 0.2. Okay, so this is our problem here. We want to solve this using Adam Bashforth as the predictor and Adam Moulton as the corrector. Okay, so the two-step. Okay, we want to use two-step. Adam Bashforth okay, which is given by yn equals to yn minus 1 plus h 3 over 2 f at n minus 1 minus half f of n minus 2. And then we can also use the two-step Adam Moulton method. Okay, so the Adam Moulton method is given as yn equals to yn minus 1 plus h 5 over 12 fn plus 2 over 3 fn minus 1 minus 12 fn minus 2. Okay, so these are the two methods that we're going to use. Now you might ask me, like, why we need to use two methods? Okay, why we must use this is as the predictor and this is as a corrector. So why we want to do that? Okay, so the few things you need to know, this is Adam Bashforth, this is explicit method, and this Adam Moulton, this is implicit method. Now, how can I tell which one is explicit, which one is implicit, right? Okay, so this fn minus 1 here refers to f of xn minus 1, yn minus 1. And this fn minus 2 here refers to f at xn minus 2, yn minus 2. Now similarly, fn here refers to f of xn yn, and this one is f at xn minus 1, yn minus 1, and fn minus 2 here means f at x. Okay, I hope the term now is clear. You don't have question regarding the function term that I'm using here. Now look at this term. This is some explicit method because, okay, so you can compare with the standard linear multi-step method, the general method, or you can see that every terms given here can be obtained and solved easily for yn. Okay, where this yn minus 1 refers to initial condition here. Now the only problem we have this at xn minus 2. Okay, now for this one, why this is implicit, look at the yn term. You have yn term at the right hand side and the left hand side here. So that's why this Adam Moulton is implicit method. Now how are you going to find values for xn minus 2 and yn minus 2? So if I'm about to draw a diagram, so my initial condition is given from the question. The step size is given for h equals to 0.1. So this is where I want to find. So how many steps I need? So I need to find x1, y1. So because it says find the solution at x equals to 0.2, right? This is my last x equals to 0.2. So that means I have 2 steps, right? So this is 1 step, h equals to 0.1, and then another step here, 0.1. So my x2 equals to 0.2. So I need to find my y2. Okay, now let's look at the Adam Bashforth here. So we need Adam Bashforth to find x and yn. Okay, so for instance, look at here, when n equals to 2, okay, when n equals to 2, look at my Adam Moulton method here. I have y2 equals to y1 plus h 5 over 12 f at x2 y2 plus 2 over 3 f at x1 y1 minus 1 over 12 f at x0 y0. Okay, so this x2 y2 here, how am I going to get it? That's why you need Adam Bashforth to predict the y2 dash here. So the y2 dash is given by the Adam Bashforth, which is y1 plus h 3 over 2 f of x1 y1 minus 1 over 2 f of x0 y0. Okay, so this y2 dash and x2 dash can be obtained from my Adam Bashforth, so that this f of x2 y2 I can obtain once I obtain the value for y2. Now what about this x1 y1 here, this value here? How are you going to find out that value? So for n equals to 1, I need to use any RK method as the starter. So I'm going to use trapezoidal rule. Let's see. Trapezoidal rule to find y1. Okay, once you use trapezoidal rule, one step where for n equals to 1, right? Yeah, I've already written here. For n equals to 1, I'm going to use trapezoidal rule, which is order 2. Now I need to say that this method is order 2. Two-step Adam Bashforth method is order 2. So the starter, you can use midpoint rule or trapezoidal rule. Okay, so you get the idea now. So let's solve this for the given problem here. Okay, and we're going to solve that for the given problem. Okay, so what is my trapezoidal rule formula? My explicit trapezoidal rule. So this is my this is the Boucher tableau. Okay, from the Boucher tableau, I need to write down my defining equation. Okay, so let's write it. y1 equals to y0. What is f1? F of x0 y0. So this is 1, right, in 4 decimal places. This is f at and x0, y1. So I have negative 2y plus e to the power of negative 0. Okay, this is the problem. What is this? This is the problem that you want to find the function given. This one. Okay, now I have already done this earlier on. So by quick calculator, if you use it, you'll get minus 1. Now I want to look at the second stage, y2. y2 here is, this is my y1, this is my y2 here. Okay, y2, so we have y naught plus h of f1. So y naught, which is 1, plus h is 0.1. Now f1, which I've already found, minus 1. So I have 0.900. Okay, and lastly, my update. No, before that, I need to find f2, function at y2. So f of, refer to my c value, which is my x0 plus h y2. So it will be x is 0, h is 0.1, y2 is 0.9. Okay, put that to the function, which is negative 2y plus exponent negative 0.1. Okay, by quick calculation, you have 0.8952. Okay, that's good. Lastly, my y1. Okay, so we want to find at n equals to 1, one step, right? So y1 here will be y naught plus half h over 2 f1 plus h over 2 f2. Okay, so b1 is half, b2 is half. So this is what you get. Now 1 plus 0.1 over 2 f1. What is f1? Negative 1 plus 0.1 over 2 f2, which is this one. So negative 0.8952. Okay, so pressing the calculator, you should get 0.9052. So this is my y1. That's awesome. So, and obviously you also need to find my x1, which is x0 plus h, which is 0 plus 0.1. 0.1. Okay, I've obtained the value at y1 and x1. Okay, that's cool. So, which means we are halfway there. So, I've obtained this value here using trapezoidal rule. Okay, so what I need to update here. So, remember, I need the trapezoidal rule to find my f as x1, y1. So, in other words, this is the function. You can call it f1 or f0, f2, so whatever. But so this is what we want. So what is f of? So I'm gonna call it. Let's say I'm gonna call it f1. Okay. So my f, or maybe f, small f, 1, which is f at x1, y1. So f at x1 is 0.1, y1 is 0.9052. Okay, so we have negative 2y plus exponent negative 0.1. So that will give you negative 0.9056. Okay, so good. Now with that value now, I can find Adam Bashforth when n equals to 2. Okay. Okay, so now continuing our solution here. So we want to solve the problem at x equals to 0.2 using Adam Moulton. So, but we need the help of the Adam Bashforth as the corrector. So for n equals to 2, Adam Bashforth, I've written earlier on here, y2 star equals to y1 plus this whole thing, right? So I can factor out half if I want to. Okay, let's do that. So for n equals to 2, we want to find y2 star equals to y1 plus factor out half. So I have h over 2 3 times f of x1 y1 minus, I think it's a half of, where is it? So factor out half, right? So I have half of x naught y naught. Okay, look at that. So f of x1 y1 we have already obtained here. Okay, now what is f of x naught y naught? That's the initial, so we can do that. So y1 here refers to my RK method as my starter. So 0.9052 plus 0.1 over 2, 3 times this value, negative. Don't forget negative, else you're going to get the whole equation wrong. 9056 minus, now what is f of x naught y naught? I've already found it earlier on, this one, right, which is negative 1. Okay, negative 1. Okay, I got all my bracket right. Okay, now all I gotta do is simplify this. You can use a calculator online, or I don't know. So what this is. So I've done this earlier on, so I can just put it in my value for you to compare. Okay, so 3 times this plus 1. So negative 1.7169. Now if you stick with 4 decimal places, it should not give you more or less. Okay, so using the calculator, my y2 star, or whatever you want to call it, that is not the same with my Adam Moulton y2. Okay, so this is my y2 star. Okay, now what is f2? I mean x2 star. X2 star is 0.1 plus h, which is 0.1. x1 plus h, which is 0.2. So I have obtained my f at x2 star, y2 star, which is f at 0.8194. Sorry, x first and then y. X, which is 0.2, 0.8194. So put in the function, which is negative 2y plus exponent negative x. Okay, what do you get? So 0. I think it's a negative 0.8201. Okay, so this is my f of x2 y2 star. Now why do you need this value here? To approximate using Adam. There you go. This value is secure. Okay, so I've obtained this value when I want to solve using Adam Moulton to find the real y2. And x1, y1, you've already found it earlier on, and this is at initial. Okay, let's find my y2, the real y2. So therefore, my y2 by the Adam Moulton. Okay, Adam Moulton given by y1 plus h 5 over 12 f of x2 star y2 star. This is the one you predicted using Adam Bashforth, plus 2 over 3 f of x1 y1. This is the one you obtained by using trapezoidal, and minus 1 over 2 function at the initial. Okay, so we have all this information that we have obtained earlier on. You should be able to find y2. So which is y1, I've obtained earlier on 0.9052. 9052 plus 0.1. 5 over 12. F of this is this one. Negative 0.8201 plus 2 over 3. Now this is f of x1, y1. I think I've got it earlier on. There you go, this one. Negative 0.9056. Negative 0.9056 minus 1 over 12. Now this is also negative 1. So I've obtained earlier on f of x naught, y naught, which is this one, okay? Or earlier on I've also obtained it, which is this value, f of x naught, y naught, which is negative 1. Okay, so all you gotta do is use your scientific calculator or MATLAB or online calculator to find this answer, okay? So 0.9052 plus 0.1. Now I've done this earlier on. This time this should give you negative 0.3417 plus this one will give you negative 0.6038, and lastly 1 over 12 plus negative 1 over 12, 0.0833. Is it 4 decimal places? Yeah. Okay, so my final answer, y2 by the Adam Moulton, is 0.8190. Okay, so this is at x2, which is x1 plus h, 0.2. So the solution at y 0.2 by the Adam Moulton is 0.8190. Okay, so that's the approximation. Now you can get 0.8191 or 0.8189, I mean plus minus, depending on how accurate you stick with your decimal places. That's okay. Now how can I compare the error? How to find the error? How do I find the numerical error? Okay, so how do I find it? So the problem you are given is this one, right? First order, y prime equals to negative 2y plus exponent negative x with the initial condition. Now this is first order. Now I can use integrating factor, right? So arranging this will give me y prime plus 2y equals to exponent negative x. Okay, so what is my integrating factor here? So my mu x equals to exponent 2 dx, which is integrating 2 will give me x, so exponent 2x. Now multiply this equation on left and right with your integrating factor. So integrating factor if, exponent 2x. So I have exponent 2x y prime plus 2 exponent 2xy equals to exponent 2x multiplied with exponent x. Okay, now what do you do here? So this term here is the same as d over dx e to xy. I don't know why I have too many brackets. Okay, I don't need that many brackets here. Okay, this is the way you read it. Okay, meaning when I use product rule to differentiate this, you will get this term. Okay, let's check. So y prime exponent to x, and then differentiating exponent to x 2exy. Okay, which is correct. Now this term here, what do I get when I simplify? Exponent x. Okay, so integrating left and right, I have e2xy in x plus c. Okay, looks like you can find my exact solution. Yx equals to divide everything by exponent. X divided by exponent 2x. We have exponent negative x plus c exponent negative 2x. Now this term is a constant. Okay, it's a constant involving term, but we know the when x equals to 0, you have exponent negative 0 plus c exponent negative 0 equals to 1. So what I have here, this is 1 plus c equals to 1. So c equals to 0. So the term involving c cancels out here. Therefore, my exact solution is given as exponent negative x. Okay, so this is my exact solution. Now, what we obtain is the solution at x equals to 0.2. So what is y? 0.2. Exponent negative 0.2. So use your calculator and you get 0.8187. Okay, let me just get exact accuracy. Okay, I can go to my online here, and I love to use Desmos scientific calculator. So okay, so what do you get? Exponent e to the power of negative 0.2. Just want to see, yeah, 0.8187. Okay, that's okay. Now what you do here, we want to find the numerical error, right? So what is error? Numerical error. So the error is, my spelling is not correct. Okay, the error is given by the absolute value of the exact minus approximation. Okay, the approximation is by the Adam Moulton. This is the one we got. Okay, by the Adam Moulton is 0.8190. Okay, so let's find the error now. So my exact is 0.8187 minus 0.8190. That's why you need the apples sign, or you can take the big number minus with the small number. Okay, 0.8187 minus 0.8187 minus 0.8190. So you get, there you go, with the absolute value sign, I can get 0.0003, or 3 times 10 to the power of minus 4. 1, 2, 3, 4, which is small, which is good. Okay, so I know I'm in the right track. I'm in the right track to solve this. Okay, now what if you want to look at the solution at x is 1? Okay, so at x equals to 1 means, so I need to find for how many steps. So we find this is 0, why not? So this is x1 when 0.1, 0.2, 0.3, 0.4 up to x equals to 1. So at least we need 10 steps here. So to do that, I'm going to show you using Scilab. Okay, so let me show you how to use Scilab to solve this problem. So obviously you got to open your Scilab. I'm just going to clear my screen here. So go to sine notes. Okay, when you click on sine note, you have this sine note. Yeah, there you go. So what I want to show you is how to solve the earlier problem using sine note. Okay, so it's much easier to solve this using sine note because we want to find the solution at x equals to 1. Okay, hand calculation will take forever. Okay, let's write a command here. The command here is solve initial value problem y prime equals to negative 2y plus exponent e to the power of negative x, initial condition given using Adam. I'm just gonna write it down. Using Adam Bashforth as the predictor. Now, there are many steps. Adam Bashforth, so we need to write two step. Adam Bashforth as the predictor and two-step Adam Moulton as the corrector. Okay, so this is what we want to do. Obviously, I want to define the problem first. Okay, so to define the problem, it's a function file. So function y prime equals to f. Let's give it fn. You can also use f if you want to. X, y. Okay, so what is my function? I mean y p equals to negative 2 times y plus exponent. This is how you write exponent in Scilab. Okay, so I have defined this equation. Initial value, we'll do it later on. So I want to define trapezoidal rule. So use trapezoidal rule for n equals to 1. So I want to have a function called trapezoidal. Now, again, there are many ways to code this. You don't have to define trapezoidal as a function. You can even evaluate it once in your main file, but this will be much easier if I do this. Okay. Now for I equals to 1 to n, I have the big Y, internal stage 1, and then I have f1 equals to f of xy, and then I have y2, which is y naught, no, y plus h times f1, and then I have f2 equals to it's not f, it should be fn, because my function I've defined at fn, x plus h comma y2, and then lastly my update, which is my y1 equals to y plus 0.5 times h times f1 plus f2, and then x1 equals to x plus h. Okay, so this is trapezoidal rule. So this is my output as x1, y1. So this is one step. Now again, all this code here, I mean whatever I've written here, it should be exactly the same like what I have explained on my whiteboard. Where is it? Let me just find it. In case you're wondering, where did that equation come from? This one. Okay, y1 equals to y naught and so on up to y1. Okay, so please do that. Now the next part is to define the Adam Bashforth Adam Moulton. So I need to have another function file called xy equals to Adam Bashforth Adam Moulton. You can name whatever you want actually, but make sure when you are calling that function, it should be the same name. Okay, so now this is very important here. So the the first step is by the trapezoidal rule. So we need to call that function. You can copy this one. Okay, I'm gonna put it here. Copy this here. So n is 1. Not much easier to do that, right? Much easier to do that. So from here we have f naught equals to fn, which is x and y. So this is my, okay, what is this f naught here? Okay, let me just write it down on my whiteboard so that it'll be easier for you to code later on. So what I want to refine here, so I'm going to refine this as my f naught, f1. This is f2, this is f1, this is f naught. Okay, so easier for you to program in Scilab. So my f naught is f of x naught y naught, f1 is f of x1 y1. So that's what I'm gonna do here. So f1 equals to f of fn, not f, x1 y1. Okay, so this is my function evaluation for my f1. Okay, now the rest I'm gonna compute using two steps. I is 2 up to n is using this Adam to predict this. So I'm going to predict yp for predict using Adam Bashforth. So y1 I'm using, so obviously this y1 refer to this y1 plus h times 3 over 2 is 1.5 times f1 minus 0.5 times f naught. So let's check this whether this is correct. 3 over 2 f1 minus 1 over 2 f naught. So I need to have h, factor out h. Okay, that's good. So what is my x2? xp. Let's say xp equals to x1 plus h. Okay. I can actually use the same x1 if I wanted to. Okay, so now we need to find f2. So this f2 here, okay, which I had like f of x2 y2, which you obtain by the predictor method, f and xp yp. Okay, I've predicted using predict using Adam Bashforth AB. Okay, so therefore, what is my Adam Moulton method? So y equals to y1 plus h multiply. Okay, so I have 5 over 12 times f2 plus 2 over 3 times f1 minus 1 over 12 times f naught. Okay, now update my x, where my x is x1 plus h. Obviously, I'm repeating here, right? So that's okay. That's okay. I just want to make sure we can clear the code later on. Okay, since I'm using so many different terms here, my y1, yp, and so I need to update it. So what happened? My new y1 was my y predict. New x1 is my x predict. Okay, and then I have my y2. The new y2 will be my y that I obtained from here, and the new x2 is my x here. And don't forget to update my f0 become f1, f1 become f2. Okay, this is everything that you need to update. Okay, so n function. So that's my Adam Bashforth, Adam Moulton method. So the rest of the coding, this is my main coding to run the function files. Okay, so define my initial condition, which is y naught equals to 1, and we have x naught equals to 0. Xn, which is my last value of x that you want to find, is 1. H equals to 0.1, and n, usually I would say the last value of y minus the initial value of the last value of x minus the initial value of x divided by h. That's my n. Okay, two things I can do here. First, if I want to produce the accuracy plot, so produce accuracy plot. Okay, so to produce accuracy plot, I need to save everything as a vector. So results, I'm going to just call it, or maybe big Y. What am I going to call it? Approx. Okay, so let's call approx. This approximation. And then H values. Okay. So how many values I want to produce is for I equals to 1 to, let's say, n. So what's my small n here? Let's say 5 points. So I equals to 1 to 5. I equals to 1 to 5. Okay. So call this function here, this one. Okay. So put it here. And this is my initial x naught, y naught. Okay, now I got to store all this value obtained as my approximate values. So APPROX equals to APPROX, and the values are all the y values. Okay, make sure how you want to store it, because you have to store in a rows. Okay, I mean in a rows. Okay, not column in this case. So and then we have h values. It's my step size. So I have h values and my h. So the accuracy plot here refers to errors versus step size. Okay. I think now what you want to do is, so this value here will give me the last value. Okay, when I is 1, the last value, look at here. So there should be whatever value here for 10 iteration, right? But the last values are going to come out as my x and y. And then I'm going to divide the h by 2 to produce the log-log plot and increase the number of n. Okay. That's it. Now, how to find the error? We know the exact solution. Z equals to exponent negative x n. Okay, the last values of xn. Now, error equals to absolute value Z minus approx. Okay, so you know that actually Z is just one value. Approximation, I have few vector. Okay, but Scilab should be able to do that with no problem. Figure 1, and we have plot log of h values with log of error. Okay, so let's put it red circle dash. Okay, I guess we are almost there. Now what I want to do here, I mean, make sure you label your graph, right? So x label is which is a log of step size, which is log of h, and then you have y label, which is the log of error, log of error, and the title, the accuracy plot. Okay, so you can put a grid if you want to. X grid will give you the grid. Okay, let's try this. If there's an error, we can fix this. So I'm gonna run it, this one, save it in somewhere here. Okay, call it, yeah, accuracy underscore, that's fine, or accuracy Adam molten. Okay, if you have error, the graph will not produce, but that's okay. We're going to fix the error. Okay, look at here. You see that line 27 for 2 to n. It should be I equals to 2 to n. Okay, we can fix that easily. I equals to 2 to n. Okay, let's run it again. There you go. So I can see that when my x is 3, x3, and then 4. So x2 minus x1, which is 1 here, that will give me 8 point something and 10 point something. So which is giving you a slope of 3. So this says that as the step size reduces, the error decreases. The error is very small. It's a log 10 to the power of something here. It's very small. Okay, so this is the accuracy plot you can get by using Adam Bashforth, Adam Moulton. Okay, now if you want to find the last value of this, so I can actually save all this. So you just gotta display all this approximate y and x if you want to produce the 5 values, or if you can also do the graph. This is called the behavior plot. So usually I'll do it separately, but let me just show you how this graph look like for the behavior plot here. So what I need here, so I just need this value here. That will give me just the last value, okay? And so I need to save all this value here. So just put it at y out equals to y, this y here, all this value. Y out I equals to my y prime. Okay, meaning I'm going to give it all in a transpose. X out I equals to x. That will give me all the value. Then I need to define it another one called x out, y out. This is why I say you do it separately, okay? Because the behavior plot means I want to produce the plot of all these values of x and y. Okay, so this we have x out, y out. Now, so let me just test it. Display y out. So I should get few values of x, y out here. Look at that. Okay, few values. This is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 value. I guess this is should be, this is the initial. By right, this should be my trapezoidal because my eyes start from 2, right? So my y1 should be trapezoidal. So I can do that actually by defining here what is my y out here. So I can say y out 1 is my, what is it? y1. Okay, from the trapezoidal. Now when I is 2, I have my so best way to do is this, I don't know, I'll just gotta try it and see. Yeah, that's automatically fixed that y1. Okay, that's good. That's good. Okay, so what you do here now, I'm showing you how to do the behavior plot, okay? So what's the exact solution is here. So we need this. So we need this to here. I mean, I just need exact. Okay, so let's say exact1, because I already defined exact there. It's my exponent negative x out, all my x value. So my x should be from 0 to 1. Okay, if you're not too sure, gotta display this x out. I'm going to remove, comment this term. And let's see what are the values of x out appear. There you go. See that? 0, 0.2. Where's my 0.1? Okay, so I need to do the same thing I did for my y out here. Say that x out 1 is my x1, meaning the first value is from the trapezoidal rule, the rest is from this loop here. Okay, so this is my exact solution. Now you can do figure 1. So I'm going to change this to figure 2. So figure 1 is the plot of x out with my y out. Let's make it blue x dash. And the other one is x out with my exact. And that's going to be red circle dash. Okay, so let's label. X label is my x values, and my y label is my approximation value. Okay, now we need a legend here because there are two graphs. See, I have two graphs here. One is the approximation, one is the exact. So the first one is my approximation, and then the second value is my exact. Okay, let's and don't forget the title, the behavior plot. So what's the behavior plot? Okay, you'll know that soon. Okay, let's look at this. Okay, where's my graph one? Oh no, something is added. Oh, there you go. Okay, this it's not quite right here. We gotta fix this. Let's fix this. Okay, how to fix this? So we have x and y, x and x exact. So let's run it again. Yeah, I can see the graph changing, right? But something is wrong with the exact solution. The exact solution is not giving me what I want because let me just clear. Okay, so to make it do this, clear all, clear screen, clear figure. Now I'm going to run it again. Okay, so this is my exact one and I'm plotting exact here. So that's the problem. So put exact one. Okay, so because it's going to get confused with this value here. That's why I got to rename it. Okay, so this, make it small letter. Okay, and this one is z1, z1. Okay, let's run this, save. There you go. There you go. Look at that. My approximation and my exact solution, they overlap. So my behavior plot tells me that as the time, which is the x, increases, my approximation is exactly the same with my exact solution. Okay, so this is usually you can tell whether your approximation is correct from this behavior plot. With this accuracy plot tells you the order of the method by taking the slope. Okay, so the slope of the method is 2. That means the Adam Bashforth Adam Moulton gives you order 2. Okay, so let's this is the code. We have a behavior plot and we have the accuracy plot given here. Okay, so if you look at my coding here, obviously they are all fit in one file, right? So if you want to tidy this up, you can do it. You can give the function file in a separate synode file and just leave this main coding. As long you have the name written correctly, the code will remember the function and run this file. Okay, and you can also see that I have to redefine my many time here. Okay, this xy is for my xy value, the last value given. But if I want to store it as a vector for n values, I need to do like this. Okay, students, so that's all for today. How to show the behavior. I forgot I here behavior plot and the accuracy plot for solving this Adam Bashforth as a predictor and Adam Moulton as the corrector. Okay, so I'll share with you again in the next lesson if you have any other questions regarding this topic. Okay, bye for now.